Okay, still in the process of doing some grading, so I know I'm a little behind on that. My apologies, but we're near the end anyways. So what I'm getting at is any outstanding assignments will be graded by the time we come back from break. Okay, today is the day that we tie everything together so you can kind of understand what the heck influence lines are all about. And there's some really cool applications of influence lines. And when I say cool applications, there are really two applications. And I would argue that the second application is more important than the first, but the second application is also impossible without the first. So let's get into it, and I want to dive right into it as quickly as possible. So I'm not going to spend a lot of time talking about the Mueller-Breslau principle, which I think by now everybody's pretty familiar with. That's the technique that we use to construct the influence line by removing from the structure the ability to resist the response of interest and then moving the structure through a unit deformation at that point. Whatever the deflected shape looks like, that's the influence line. I'm not going to spend too much time talking about the rules for constructing the influence line for reactions or the rules for constructing the influence lines for shear and moment. I just want everybody to be comfortable with them, which I am hoping by this point you are. Without getting marred up in the details, is everybody okay with that? Anybody have any questions? Okay. Up until now, influence lines are pretty little pictures of lines that really haven't done much for us. So what the heck are we going to do with them? So there are two applications of influence lines that are connected, but you need to understand both of them. And the second application, which is by far the more important one, is impossible without the first. So let's talk about the first. The first application of influence lines is that it allows you to perform structural analysis directly. Okay? So one of the first applications is maybe replacing the equations of equilibrium. Here's my point. What is an influence line beyond just what the Mueller-Breslau principle allows us to use to easily construct it? The influence line is a response of interest due to a moving unit load. I take this unit load and I move it across the structure and I record the response. Well, if I know the response due to a unit load, don't I know the response due to any load? Let me ask you a question. This table, if I put 1 pound in the middle of this table, what are the reactions on each end? They're a half, right? What if I put 70 pounds right in the middle of the table? What are the two reactions? So how did you get that 35? You took 70 and you multiplied it by 1/2, right? Because 1/2, here's another way of thinking about it. 1/2 is the ordinate, the value on the influence line when the load is right here. I propose that if you have a problem like this, where you've got point loads and distributed loads and so on and so forth, you can use the influence line to directly perform the structural analysis. The way that works is you take the point loads and you multiply them times the correlated values on the influence line, and then you take the distributed loads and you multiply them by the area under the influence line, and you add it all up. And that result is the same result that you would get if you just did the problem like we've been doing this whole semester in CE 312, okay? I'll give you a sec to write this down because I see some folks already doing that, and I'm going to show you how this works here in a little bit with a very basic example. And there's nothing like super magical about this formula. You're going to see how it works here in a second. Excuse me. Everybody good? All right. Here's the problem. Now let's take influence lines and throw them out the door. Ignore the concept of influence lines for the next minute or so. I have a beam. It is simply supported. I have a hinge support at A. I have a roller at D. I got a distributed load on there, 2-point loads. How many people in here are confident that they can determine the reaction at D? Forget influence lines. Can you tell me how to compute the reaction at D? What's an easy way of doing that? Maybe some moments a day? Okay. let's do that, and let's see what happens. What? So here's the problem. What can I do with that distributed load? Collapse that into a single point load, right? How much is that point load going to be? What's 1.3 times 20? Oh, there you go. I'm saddened that I see a number of people do not bring their Casio FX115 ES Plus or similar scientific calculator. I'm saddened by that. How far from A do I place that collapsed load? What was that? There we go. So this reaction here, AY dy. So maybe what I'll do is I'll sum the moments at A. And what do I get? 26 times 10. 25 times 40. 42 times 60. And then dy times 80 opposing it. All right, so what do we got? 26 times 10, that's 260. 260, not 266. 1,000. And then 2520 for that one. So if I sum those up, I get 3780 is dy times 80 feet. I get that. Now I did that real quick, but I have got to believe at this point that that is easy. I mean, is it? If it's not, if there's something missing, let me know. Because I don't want that to be the barrier for what comes next. Let me see something. I'm going to have to screen cap that again because I'm lazy. Bear with me. Oh. You know, every now and then, you could just work. I'm going to close that. It's like if we were playing, what is it, D&D, it'd be like chaotic neutral or something. I'm a dork, I know. I put Yoshi in my statics notes today. So I put Yoshi in, we're doing friction, and there's a block, and so like Yoshi's going to push the blocks. Again, I'm a dork. All right, let me stop for a sec and see if this made sense. Is everybody okay with this? Now this is the statics equilibrium approach to determining the reaction at D. Now I'm going to show you the influence line approach. And it's crazy that this works. At least the first time that I saw this, I was like, you've got to be kidding me. Watch this. Now, this problem is focused on determining the reaction at D. So maybe what I will do is draw the influence line for the reaction at D. Can somebody tell me what the reaction for the influence line at D is going to look like? Say it just like that. Okay. All right, hold on. So, like that. So this is the influence line for dy. So this is 0. This is 1. Now, let's use a little bit of common sense here. This beam is 80 foot long, and this is 20, 20, 20, and 20. So what do you think the corresponding points on the influence line are here, here, and here? Quarters, right? So that instead of 2 quarters, we'll say 1/2. 3 quarters? Is that fair? Okay. Now, what is the area of that triangle? All right, you say 5. So how are we doing that? We're taking 1/2 the base times the height. So 1/2 of 20 is 10. 10 times a quarter is what? 2.5. So forgot the half. So 2.5. Is that a fair statement? Watch this. I'm going to take the distributed load, multiply it by that area. So just watch me. Don't write anything down yet. Just watch this. I'm going to take this distributed load, and I'm going to multiply it times that area. Now just watch. I'm going to take 25, and I'm going to multiply it by 1/2. And I'm going to take 42, and I'm going to multiply it by 3 quarters. So just watch me up here. The distributed load times the area, 25 times the value, 42 times the value. And then I'm going to take these, and I'm going to add them up. And I propose this is dy. What is that? Yeah, 1.3. That's the magnitude of that load. If I was a betting man at the roulette table, I would say you got that. I don't know about you, but the first time I saw that, I was like, you got to be kidding me. How simple that is.
So you use the area of that first one because it's a distributed one?
Yes. What you would do, that's, okay, so to clarify, we're taking the distributed load times the area where that distributed load occurs. So if the distributed load went from A to B, we would take that area, the area of the triangle associated between A and B. That's crazy, isn't it? No equations of statics, nothing. Just draw the influence line, boom, there's the answer. Kind of valuable if the loads move, right? What if I put the loads somewhere else? What's easier, this or that? I think it's a lot easier. I want to stop and make sure that this makes sense because I don't want to move on to application number 2 if application number 1's a little fuzzy. What do you think? Okay. Now, once you're done writing, we got some concepts to get through. So you want to put your thinking cap on and pay attention to this part. All right, pay attention. So the first application of an influence line is to just do the structural analysis for us. The second application is worst case response. Why did we start doing all this stuff with influence lines to begin with? What was the whole point? The whole point was to deal with moving loads. So as analysts, what that means is, here's a bridge, here's some moving loads, where do I put those loads to generate the worst case response? That's what I'm interested in as an analyst, because I need that for design. Now, influence lines, and this is what our last example just told us, we can use influence lines to do that analysis for us. For concentrated loads, so what does that mean? Concentrated loads, if I have a moving load, let's go back to that previous example. Where would I place a single concentrated load to maximize the reaction at D? Imagine there were no loads on this beam and I had a single 50 kip load. Where would I put that 50 kip load to maximize the response at D? At D, right? Make sense? That's what the influence line tells us. And now I could just say 50 times whatever the value is on the influence line, and that'll tell me the response, right? What if I had a distributed load, like a 2 kips per foot distributed load? Where would I put that distributed load to maximize the reaction at D? I'd put it everywhere, right? I'd put it along the entire beam, because that will generate, the more distributed load there is on that beam, the bigger the response is at D. Make sense? Now, what this will result in is an envelope of results. So instead of an answer, we're going to get a range of answers. So you're probably like, wait, what? So let me give you a quick example. Let's look at this beam. This is a simply supported beam, and I have drawn the influence line for the shear at a given section. In this case, it's a 60-foot long beam, and I drew the influence line for shear 20 foot from the support. So we have a total jump of 1. This line and this line have the same slope, and so this is a -1/3, this is +2/3. That's after I did all the math. Is everybody like okay with that? Like that should be easy to understand? Okay. Because the influence line has positive and negative values, there's negative values on the influence line and there's positive values on the influence line. Because it has a range, we can generate a range of responses, okay? So I want to think about this. If I had a distributed load of, let's say, 2 kips per foot, where do I put that load to generate the worst case scenario? Or maybe I should say worst case scenarios, okay? And I want you to think of distributed loads as sort of like paint that you can put anywhere on the beam to generate the worst case response. I want you to think of distributed loads as traffic on 3rd Avenue. There's not anything that says the traffic all has to be in one line, right? I can have a bunch of traffic here, a bunch of traffic here, like here's a line of cars, and then there's a gap, and here's another line of cars, and here's a gap, another line of cars, right? If we're talking about a bridge on 64, you know, I could have some parts of the bridge that are loaded, some that aren't. And so the idea is, where do I put that load to generate the worst case response? Well, the influence line tells us where to do that. We place the load where we need to generate worst case response. So watch up here. Here's the example beam. Here's the influence line. Where would I place the load to generate worst case positive shear? I place it here. Everywhere that there is positive ordinates on the influence line. So this is where I would place the load to generate the worst case shear right there. And what is that shear? How would I determine the shear right here under this load placement? We just figured that out. Take 2 times this area. And so that is a maximum positive shear of 26.67 kips. Now, pop quiz. Where do I place the load to generate the worst case negative shear? On the left side of the section. So this is the load placement for maximum positive response. That's the load placement for maximum negative response. Okay? And how do I determine that response? Load times the area. There's a little negative there. It's kind of fuzzy there. It's kind of hard to see on this screen. So what I propose is that we have a maximum, I'm calling it maximum positive and maximum negative. This is like an extreme positive shear of 26.67 kips and an extreme negative shear of negative 6.67. So I propose that this point on the beam, if we have a moving distributed load, it's not that it's going to see a given shear value. It's going to see a range of shear values. And that range is going to be anywhere from here to here, provided that 2 kips per foot is the load that we're talking about. That's the envelope of shears that that particular point sees. What we as bridge engineers do is we do this calculation over and over again. We do it typically at 10th points. So think of this point as this point here is like 0.33333L, right? Because the beam is 60 foot long and we're drawing the influence line at 20 feet. What we typically do as bridge engineers is this is a 60 foot beam, we would do this at 0 feet, 6, 12, 18, 24, 30, 36, and that's enough to represent the range of values that we need to do for designs. I'm doing this for one, we would just repeat it over and over again. That's what computers are for. Does that make sense? Is everybody okay with this? Now, if you're okay with that, I'm going to introduce you to some new terms. Next semester in steel design, we're going to get a lot of familiarity with these two terms. These are dead loads and live loads. Now, we are going to handle them in a much more simple fashion in steel design than we do in here. Because in steel design, we're focused on the design. So we're not going to deal with the analytical complexity that we do in here. But I want to introduce you to some terms related to design, dead loads and live loads. Let's talk about dead loads. Dead loads are permanent loads that remain stationary. An example of a dead load for a beam is its own self-weight, right? If you have a beam that's a W24 by 76, that beam weighs 76 pounds per foot, and that 76 pounds per foot is along the entire beam. So an example of a dead load would be the self-weight, which is applied everywhere. So if I wanted to deal with this, and I wanted to deal with dead loads, I would not say the dead load acts just here or just here. The dead load acts everywhere. So I would have to take 2 kips per foot times the sum of these areas, this positive area and this negative area, because it's everywhere. Dead loads are applied everywhere. Live loads are applied anywhere. Live loads are transient loads. They are moving loads to generate the worst case response. An example would be traffic on a bridge, which can be anywhere. So we as the analysts put that load to generate the worst case response. Dead loads generate a single answer. Live loads generate a range of answers, an envelope. Does that make sense? Is everybody okay with that? Let me stop and make sure conceptually that that makes sense. Okay. Okay, let's look at this beam. Now, before we dig into this example or dive in, we have already looked at this beam. We have already drawn influence lines for this beam. So we're just going to use them. We have drawn the influence lines for the shear and moment right here. We did that a couple days ago, or a couple lectures ago. I want to know the shear and moment due to a dead load of 1.2 kips per foot, and I want to know the shear and moment due to a live load of 1.6 kips per foot, which is a distributed load, and a 25 kip load, which is a concentrated load. Okay? So there's a lot going on here, but it is incredibly simple. It is much easier than you probably think. Okay? First off, let's recognize the fact that we have already done the influence lines. So here's the problem. We already drew these. If you need to recopy these or whatnot, go ahead. We got time. But we already did these. Now, before we start the dead load, live load assessment hullabaloo, I want to do some area computations. Let's start off with shear. What's the area of this triangle right here? 1/2 of 6 times 0.3. What is 1/2 of 6 times 0.3? And what's more important, positive 0.9. Now what about this whole triangular region here? 1/2 base of 20 times the height. So we can actually get the entire triangle in one fell swoop. What is the area of this whole triangle? Oh. 1/2 of 20, which is 10, times 0.4, I believe that's 4. Does that make sense? What about this triangle? What's the area of that? Do I have a second on that? Notice how we're dealing with an influence line, not a shear diagram, so they don't have to add up to be 0, although they do. Yeah. Let's do this one. What's this and this? Let's start off with the positive. 1/2 of 20 is 10, times 4.2 is 42. This is negative 24. Is that okay? Is that okay? All right. So let's summarize some things. Would you agree that for shear, would you agree with that? What about for moment? Would you agree with, oh, sorry. Would you agree with that? So, just to be clear, this is 0. This is 18. Did I do that right?
Would the A positive for shear be 4?
Well, that and that. Did I? Did I do this one right too? Okay. Keep those numbers in mind. Oh, go away. All right. Let's consider the dead load. Now, how much was the dead load? I believe it was 1.6 kips per foot. Is that a fair statement? So I propose that in order to compute the shear due to the dead load and the moment due to the dead load, what we're going to do is take this and multiply it not by just the positive or the negative, but the total area, because the dead load is everywhere, right? The 1.6 kips per foot, think of that as how heavy the beam is. So we're going to take 1.6 kips per foot times all the areas. So this one's going to be 0. Oh. This one's going to be 18. So what's 1.6 times 18? 'Say it again. 28.8. So therefore, no dead load shear at that point. There's that. And if you don't believe me, put 1.6 kips per foot on this beam, compute the reactions, draw the shear diagram, draw the moment diagram. What you'll get is a 0 on the shear diagram and a 28.8 on the moment diagram at section 1.1. Does that make sense? Any questions? All right. Now, how about the live load? How much was the distributed load for this problem? Wait. I'm sorry. Did I say the dead load was 1.6 or 1.2? Hold on. See, nobody's catching me on that. I said this was 1.2. It's like I knew something's wrong.
I feel like that's a big mistake. That counts a whole.
What's worse, I caught it though. Everybody else in here is just sitting there like it's Friday. We just want to get out of here. How many of y'all thought that?
I didn't write it down. Me neither. I was just going with the flow, man.
If you wouldn't have said nothing, we would never noticed. We could have went on with our happy day.
You'd have gone on with your happy day, and then you'd have been doing that homework assignment going, what? So what was one? Now it's 1.2 times 18.
21.6.
Okay, let's try this again. My goodness.
You put 1.6.
But that's the live load.
That is this time?
Any other criticisms?
I was just checking so we didn't get
I'm just messing with you. I'm just messing with you. Okay. Now, for live loads, we're going to get a range. So what that means is we're going to get a positive shear and a negative shear. What that means, we're going to take 1.6 kips per foot times the positive and negative areas. Okay? So this is going to be 4.9, negative 4.9. Are you understanding the concept? So we're going to do the math, and then we'll take a look at what the math means here in a little bit. So what is 1.6 times 4.9? 7.84. Do I have a second on that?
Yeah.
So VL plus is this. Now, what does that mean? Well, let's look at this. So here's the beam, and imagine that my yellow highlighter is the distributed load. Where do I place the load to generate the worst case positive shear? Well, I propose I place it here and here. Why do I place it there? Because that's everywhere that there is a positive ordinate. And how do I determine that? The magnitude times these areas. So like a checkerboard, where do I place the load to generate the worst case negative shear? I place it there. So again, think of this as traffic on the bridge. So like imagine traffic moving down the road. And if I had a chunk of traffic right here that weighed 1.6 kips per foot, that would be the heaviest shear that I could get at that point. Does that make sense? Okay. So for moment, we're going to get a little bit of a different answer. Because for moment, what we're going to do is we're going to take times the positive and negative areas associated with that. So what goes right here? 42, and over here? There you go. So I'm gonna erase these circles real quick because I'm gonna do something with them here in a second. Does this make sense? Everybody good? Okay. So what are we getting for ML positive?
67.2.
ML negative?
Negative 38.4.
So I'm going to say this is the range for the distributed load. But it's not the range for the concentrated load. Now, let's talk about that. Now, we have a concentrated load we have to move across this structure. How much is it? Anybody write that down? 25.
I have no idea, I'm guessing.
Oh, now I'm definitely scrolling up to see. Yes, it's 25.
No.
Now, just like with the distributed load, we're going to have four answers. We're going to have a positive and negative shear, and a positive and negative moment. And I propose, just like we did for the distributed load, For the concentrated load, it's going to be 25 kips times something. So do I just put these values in there? You're shaking your head no. Why?
Because that's the area.
And
You don't use the area for cost.
boom, that's 100% right. We take distributed loads, multiply them by areas. But we take concentrated loads, and we multiply them by values. Boom. So we need some values. So let's look at the shear. What is the maximum positive value on the influence line for shear? 0.4. What is the maximum negative value on the influence line? Negative 0.7. So you're telling me that this needs to be positive 0.4. This needs to be negative 0.7. So, okay, what does it need to be for the moment? What do we need to put there? What's the positive value? What's the negative value? All right. So what do we got for here? This is what, 10? What about this one? All right. For the moments. Say it again. 105. So let's see. Sorry, hold on. That's foot kips. Sorry, foot kips. So I tell you what, here's how we're going to do this. I'm going to do this. I'm going to say this is answer. We'll call this LL distributed, answer LL concentrated. But we're not done because we'll call this D. We're not done because I want to look at the very, very, very final answer. I want to look at the envelope. So I got an answer for the dead load, a range for the distributed load, a range for the live load that's concentrated. How would I determine the overall envelope? So let me drag this down a little bit. So how would I determine the worst case positive shear? So wouldn't I just add these two? But what else do I need to consider? That plus 0? Because that's constant, right? So what I need is 0 plus 7.84 kips plus 10 kips So if the dead load is everywhere and the live load moves, this is the worst case positive shear I can get. Is that fair? If the dead load is everywhere, but the live load moves, what is that? What is negative 7.84? What is 0 minus 7.84 minus 17.5? Is that fair? What about moment? Moment is the dead load moment, which is everywhere. Here, let's shorthand that a bit. The dead load moment, which is everywhere, plus, come on, my pen's failing me. All the positive moment range values. So what is that? 193.8. What about the minus? So I would take this value, which is constant, the dead load moment doesn't change, minus, what is my pen's problem with this? What is that? Say it again.
Negative 76.8.
So I have one more thing I want to show you, and then we're going to call it for today. Oh, well, we're running short on time. Very, very, very quickly. First off, does anybody have any questions on this? All right, real quick, note. If I wanted to draw the influence line for shear right here, it would look like there, right? Where would I place my load to generate worst case positive shear? Right here. Where would I place my load to generate worst case negative shear? You're shaking your head. Why? You don't have it. So the worst case positive shear is a value. The worst case negative shear is 0. You cannot generate negative shear at that point. So the VL negative would be 0. That's okay. That happens. There's nothing wrong with that. Does that make sense? Anybody have any questions on this? Did I blow your minds a little bit today? Good. All right. That's all I got. Monday, we dive into the wonderful world of AASHTO and bridge load models. That's all I got, everybody. I will see you all on Monday. Y'all have a great weekend.